Hi, welcome to learning about the periodic trends with periodic law. Answer this one question to help give you insight that it's not just facts that make the world, but we can use those facts to see trends and make predictions about many different things. So in the one you saw online with Crash Course, you saw that they talked about Dmitry Mendeleev, how he came about this idea and saw that the idea of the periodic table is this concept of periods, meaning repeating times. If you go on to take physics, you'll see that periods are the time it takes for things to repeat. So this periodic is this idea of repeating patterns. This is called periodicity. We use this to understand how things work and where things work. And so we're going to use this concept all the time in chemistry, learn about the periodic table, so we can get an idea and predict things without knowing 101 facts about everything. So we've previously seen that there's some information we can pull from this. Valence electrons, those highest occupied energy level electrons, remember, are the ones digit. For what we call the S and P block. These are kind of older terms or college terms. So the S is incorporating everything here. That's the S over here. We generally have the P block, but it really illustrates kind of more over here because the transition metals will have their own amount of valence electrons. So again, you would have the idea, number of electrons and everything. Here's 1, 2, zooming in, 3, 4, 5, 6, 7, and 8. So keep that in mind as we go throughout. Now these valence electrons are the ones that are gained or lost, which is how we make ions. So when we see that the idea of metals are going to lose electrons, that means they're always going to have a positive charge because in losing electrons they're going to end up having more protons than electrons. On the other hand, nonmetals gain electrons, and so because they gain electrons, they're going to end up having more electrons than protons and have negative charges. So I'm going to label down here at the bottom, let's go with red, that of course at the bottom here we have 1 plus, and the idea is we put the number first, then the charge. 2 plus, we'll skip over this area here, need to zoom out to see where I'm at. The 3 plus is only referring to the ones in the P block, these right here. Now, carbon, a non-metal, is going to gain 4 electrons, so that's 4 minus. Then we go 3 minus, 2 minus, 1 minus, and then the noble gases won't do anything with their valence electrons, they'll be at 0. So knowing these patterns will help us a multitude down the road, so you want to write all of this on your periodic table that you have for the year. Now let's look at these periodic trends. Now, trends are not 100%. Things like fads, they come and go, not long lasting. Trends usually last quite a bit of lasting power. And in science, these are thought of as being things that are meant to be pretty much true, but they're not 100%. Just like the trend of everyone owning blue jeans, there's someone out there who doesn't have blue jeans. They're not weird, they're not crazy. It's just not for everybody, okay? Same for like cell phones. Not everybody has one even if they can afford one. They're just tendencies for occurrences. So keep that in mind if you see numbers or values or things in other places. We're going to look at these as trends, not as everything being 100% the same way. So we see the atomic radii will decrease across the periods, so that would be across, while it will increase down a group on the periodic table. Now there's the key reason why. It's all about the structure. As we look across, this one I've drawn through here, and you can see that's generally true on this modeling of the periodic table, the fact that as we go over we're adding one more proton to each of these from the previous. However, they're on the same number of energy levels. So if the energy levels is the same, but we're increasing positive charge, that's going to pull those energy levels closer to the nucleus, therefore shrinking the size of it. As we go down, we're adding an energy level. So if I were to zoom in here, we have one energy level. Whoa, that was interesting. One energy level, two energy levels, three energy levels, four, and so on. So the idea is that we're adding one more energy level. So just as when you add another layer of clothing, your volume will get larger. The radius of the quote-unquote spherical atom will get larger. It's not technically spherical, but for our simplicity, that works great. So I want you to be able to explain the why, not just these sentences you read, but actually what I've explained over this. So if you want to hear it again, take it back and go hear it again. But you need to be able to explain not only what the trend is, but the why and reasoning behind it. Coming with any of your questions if you have trouble with remembering this. Let's take a look at ionization energy. Now you see up here I put size matters, because I'm going to explain all of these using the size of atomic size. It makes a key concept about these forces of attractions, positives attracting negatives. Essentially all of chemistry is positives attracting negatives. How much or how little they are affects everything. So when we look at ionization energy, energy required to remove an electron, that's key. If you remove an electron, you should get a positive ion. So this is all dealing with making positive ions, not negative ions. That's called electron affinity. We're not going to do that because it doesn't really play a role till you get much further in chemistry, even AP chemistry. So we see that the energy decreases as you go across a period in general. So as you go across a period, it will increase, I think I said, and that would be going across like this bottom row in this bar graph representation. And it decreases as you go down a group in general. So decreases as you go down. So the idea is why? Think about with size. As you go across, the atom gets smaller. So if you're trying to remove an outer electron, remember if you have a nucleus and then you have an electron out here you're trying to remove, if it's closer to the nucleus, its attraction is high. And so if its attraction is high, it's going to take a lot of energy to remove it. On the other hand, if we have another energy level and another one, and we're trying to remove this electron, the distance between that and the nucleus is much further. And even though the nucleus is higher in charge, the distance will make much more of the difference than the distance will. Than the amount will. So this being further away has less attraction, and so therefore will require less energy to remove. So one of the key ideas here with attraction and energy is the idea closer the attraction, higher the energy. There is a difference with the idea of attractive force and mass and distance. It's really G(m) over r squared is equal to force in general. So the idea here is that if we doubled the mass, that would double the force. However, if we doubled the distance, because it's squared, that would be 1/4 the force. So what this means is that the radius is more important than the amount when it comes to attractive force. Okay? Both will have an effect on attractive force, but it's more important the distance as opposed to the amount. If this seems a little confusing, again, think about it, ask questions in class, and we'll hash it out as you will over time. All right, let's take a look. If you remove one electron, why does it always require more energy to remove another one after it? So if we look at some examples that you have here on your paper, sodium with its 11 electrons, first ionization energy 496. The second one, after this outer energy level has been, removed since this electron's gone, that inner energy level is actually closer now. Okay? Way closer to where it's almost 10 times the amount of energy. Now if we look at something like magnesium, which has 2, we see that if 1 gets removed, 738, whatever. The second one is twice that amount. Now you might say, okay, why is it higher than the first? Isn't it in the same energy level? The idea is that the energy level is the same energy level as far as numbers go. However, when 1 electron is removed, these 2 electrons in the outer energy level are repelling each other. They essentially make the size of the energy level what it is. However, if 1 is removed, I'll kind of highlight with green, if 1 is removed, now there's not 2 repelling each other. That this one gets a little closer. I'm going to put it in between, even though it can't be in between. In which now to remove that one, because it's closer, jumps up the amount of attractive force between the nucleus and that electron. Therefore, the amount of energy to remove it increases. Likewise with the third one, now that's in a totally different energy level. That's much closer, hence the big jump. You look at something with aluminum with 3 valence electrons, somewhat triples, I don't know, another 50%, and then whoa, huge, because it's again another energy level. All the electrons want to repel each other, so if you get rid of things repelling, then the size of the shell will shrink. The ionic size will get closer, or I should say smaller, as an ion, and that as an ion being smaller, it will go ahead and get closer to the nucleus, which increases attractive force. So after 1 electron is removed, the remainder get closer because there's less repelling, so more energy is required. Again, come in with your questions. I'd like to discuss this with you, show different examples to help you understand this clearly. All right, let's look at our next trend, ionic radii. So ionic radii, width of the ion, similar to atomic, but of course atoms are not ions. Ions are atoms that have lost electrons. So I use the term differs as it goes across because it doesn't necessarily shrink, doesn't necessarily grow. So the colored items are the ions, the gray are the atoms. So they're color coded. Now the idea is why? Well, if we take a look at the metals, those are going to lose electrons, shed their outer shell. So we can see that they go from 1.34 to 0.68, 0.82 to 0.23. They shrink. Okay? However, just like the ionization energy that we looked at previously, if you remove electrons and the energy level shrinks, guess what happens when you add electrons? They're going to grow. So as 2 more electrons are added to oxygen, there's now 8 electrons in that energy level. And just like 8 people who don't like each other, they're going to spend this further way apart because there's 8 of them now, not 6. So we can see that the size of the ion, greatly increases, as holds true with this. Now again, you can see it differs. It doesn't always increase across. It kind of does. There's other reasons for this. But if we look at what we start with and what we end with, you can see that across it's going to grow. Okay? But it's for 2 reasons. Metals are going to shrink. Non-metals are going to grow. And again, we skip over all of the transition metals and lanthanide and actinides and all of that stuff. So don't worry about that. On the other hand, as we go down the energy levels, guess what? There's another energy level. So it's going to seem that they grow going down. Because this one has 2 energy levels, 3, 4, 5. So even though they're doing the same thing, as we go from one to the next, you can see that they grow in size because we're going up energy levels. Adding another layer, just like we did with atomic radii. Let's take a look at our second to last trend, electronegativity. Now, electronegativity is just a scale. Just like a 4-star restaurant, 4 doesn't mean anything technically. It does mean the best in that case. When we think of a 3-star restaurant, that's better than a 2, not as good as a 3.5, that kind of idea. But that doesn't mean a 3-star restaurant is 3/4 the restaurant a 4-star is. Just like a 2-star restaurant isn't half as good as a 4-star. So it does not a technical connection with those, but you would know that 4 is higher than 3 and so on. So on the electronegativity values, fluorine is the most electronegative, while something like rubidium would be some of the least electronegative. And that has to do, again, with atomic size. Again, electronegativity is the ability to attract electrons of another atom, okay? Not its own electrons, but of another atom. Now, this again has to deal with size. Due to something being smaller like fluorine being super tiny, its ability to attract electrons to itself is going to be very high because that distance between the nucleus and outer electrons is the smallest, which means it gets closest to any other electrons outside of its own atom's sphere. On the other hand, something like rubidium actually just goes to cesium on here. Looks like it's missing on this. Oh, it only goes to here. I see. On rubidium, it's very large. So that means any electron on the outer part of it, from another atom, is going to be hard to attract it because of the greater distance. This again is another illustration that the distance is a much bigger influence than the amount of positive or negative charges. So smaller size, closer to the surface as you go across the table. We know that going down, they get bigger, so again that distance is going to make it harder to attract electrons. D and F block elements, different than the S and P. We're not even going to cover that. Just like you can see across what's called D block, the middle, it varies. There's lots of differences. That's not going to be something we'll take a look at. That's more of a college level chem stuff. So electronegativity, big feature. These trends are going to help us predict many things as we go going forward. That's why it's important that you know all of these trends, what they are, and how they affect this, because that affecting is going to help you explain why we see some other things like reactivity, conductivity, heat, thermal conductivity, all these different properties that we see in chemistry. Be sure if things are not seeming to make sense, come in with questions. Let's have a discussion as a class. It's great to go over many other examples if you'd like. And we come to our last trend, reactivity. Now, reactivity is going to split into 2 different categories. The idea that for metals, just really the S block, and again, you see we don't include hydrogen. Reactivity increases going across, increases down, decreases across. You could also say this is the most reactive, francium, and beryllium is the least reactive of these. Because again, that would be the opposite. So you could say reactivity decreases in this direction. So you can label these things many different ways. We're going to talk about them in period and group trends though, so you might want to keep it straight with that. Now, the idea is that fluorine's the most reactive non-metal, again, different than the metals. So reactivity decreases going down and increases going across. So going across increases, going down decreases. Again, going over decreases, reactivity increases down here. So there's many different ways you can say it, but you want to talk about period and group trends. We usually have to talk about going across the periodic table, going down the periodic table. You see all these things white? These all vary. So that's why there's a lot to chemistry that we don't go through in a general chemistry class or even honors. But the idea is that we can use these basic trends because we deal a lot of our chemistry with these blue and pink labeled atoms. Please come in with your questions. Again, all of these trends, you need to know what the trends are and be able to freely explain the why. in order for me to understand that you've met all the standards. Coming with your questions. I hope to see you soon.